Okay, so today we start with our new chapter in chemistry, that is sulfuric acid. This is the fourth chapter and the last chapter in case of study of compounds. So in the study of compounds we had four chapters. The first three which we already completed is HCl, that is hydrochloric acid and hydrochloride gas, ammonia and nitric acid. This one is the fourth one, which is sulfuric acid, the last chapter in study of compounds. Coming to the discovery of sulfuric acid was initially called as oil of vitriol. So it was called oil of vitriol. In fact, it is seen that all the sulfates are called as vitriol. So that's why when you say green sulfate, blue sulfate, there's the green will be iron sulfate, blue will be copper sulfate. So all these vitriols are nothing but sulfate. So here we are saying oil of vitriol, which is nothing but the sulfuric acid. It was initially prepared by distilling green vitriol, that is FeSO4.7H2O, and hence the name oil of vitriol, because it was formed by FeSO4. That's why the green vitriol, that's why it was named as oil of vitriol. Hence the equation was FeSO4.7H2O gave me Fe2SO3 plus SO2 plus SO3 plus water, giving me as the result H2SO4 plus 13 water. Occurrence wise, sulfuric acid occurs in free as well as in the combined state. In case of a free state, it occurs in minute traces in hot springs. Now normally all the hot springs, what you see, the hot springs are the one which may have a certain amount of sulfur content in the soil. So if you actually, when you visit any hot spring, you can smell the sulfur around you. So that is why most of the hot spring would have sulfur content in that, and that's why those hot springs will have certain quantity of sulfuric acid present in them. It is also formed during sulfide beds, that is hydrolysis of iron pyrite. Now iron pyrite is a mineral ore of iron. So this iron pyrite is FeS, so that sulfide of the iron pyrite is also going to give you the sulfuric acid at certain places. In a combined form, it occurs as salts in minerals such as metallic sulfate. So all metallic sulfates which are there, they will be containing the sulfuric acid. So that's why metal sulfates will be having the H2SO4 in a combined state. So in a combined state, it is found in the salts of sulfates. Now the preparation. Now in this chapter, we do not have the laboratory preparation of sulfuric acid. There is no laboratory preparation of sulfuric acid. We only got the industrial process of manufacturing of sulfuric acid. So in case of general preparation, so they are given four different ways by which the H2SO4 can be generated. That is what we are going to take now. And that is, first one is the reaction. If you remember the reaction of the sulfur with nitric acid. Now we learned earlier in the earlier chapter that nitric acid, when it reacts with non-metals, it will give you NO2 plus H2O plus some kind of a like sulfur है तो sulfur dioxide जैसा देगा, but it is going to form into sulfuric acid. So we have the first one as S plus HNO3 will give me as the product as NO2 plus H2O plus H2SO4. The balancing would be 1612, that is 1612. So that is the so we can say by concentrated nitric acid reacting with sulfur gives you sulfuric acid over here. So conversion of nitric acid to non-volatile sulfuric acid, that is action of heat on nitric acid and sulfur. Second is passage of chlorine through an aqueous solution of sulfur dioxide. So when you have chlorine which is passed through Cl2 SO2 plus water H2O, this is going to give you in the resultant as 2HCl plus H2SO4. So this is the reaction which gives you sulfuric acid, that is reaction of chlorine with sulfur dioxide and water. The aqueous solution is sulfur dioxide. Third one is dissolution of sulfur triode in water. That is a very easy one. SO3 plus H2O is going to give you H2SO4. So that is the direct thing over here. That is sulfur trioxide and water is going to give you H2SO4. And finally is the hydrolysis of sulfuryl chloride, that is SO2Cl2 plus 2H2O. In fact, it is almost the same, but only thing is this is formed into a compound, that is hydrolysis of sulfuryl chloride is formed. Otherwise, the reaction is the same. It is going to give you the same thing over here, that H2SO4 plus 2HCl. So this is the same reaction, but only thing is that here there are two different compounds. This is a aqueous solution of sulfur dioxide, whereas this is the aqueous solution of sulfuryl chloride. Okay, so that is how it is going to be prepared. So preparation of H2SO4 in the laboratory is going to be any of these methods of usage. Okay, but there is no such like a laboratory preparation. It is just a equation for preparation. We now come to the manufacturing of sulfuric acid, and the manufacturing of sulfuric acid takes place by a process called contact process. So the process over here is going to be contact process. A very important part. Contact process, one of the important part of the chapters of 4 compounds. So in the if we consider this thing in a proper one by one step by method, so we see that there is going to be 4 different processes. The first process will be the production of SO2. So first thing what is going to be there will be two things, what is A and B, which are going to be a blower and a sulfur, or you can say a pyrite burner. So there will be 2 things. So that will be we are taking over here as first thing is A, which is a blower. This blower is going to burn a place over here. This is the B part, which is nothing but the sulfur. So we are going to take it as a burner or sulfur. We are going to take sulfur over here. Okay, the blower is going to give you continuous amount of blowing of air, so that passage of purified air and oxygen is available to that particular sulfur which is over here. So this is going to give rise to what we call it as the step 1, that is S plus O2 giving me SO2. So sulfur is going to react with the air which is over here, because you are going to burn this thing, you are going to heat this thing. So burning sulfur is going to be heated over here. Now the same process can also be done with an iron pyrite. So we can take iron pyrite and oxygen, we are going to get the same result over here. So this will be 4 FeS2 plus 11 O2 will give me 2 Fe2O3 plus 8 SO2. So these are the reactions which are going to take place for in this particular section. This is nothing but this section over here is called as the production of SO2. So the first step which is going to be there is the production of sulfur dioxide from sulfur, and that is done either in 2 ways. You are taking to take pure sulfur and going to use air which is going to have 20% oxygen in it. So accordingly we'll be having oxygen plus sulfur to give SO2. If you don't want to use pure sulfur and you want to use an iron pyrite, so anyway in the iron pyrite you are removing the sulfur from it, so you can use the iron pyrite, and the sulfur from the iron pyrite is utilized over here to give rise to SO2. So SO2 is going to be formed by 2 processes over here. The next thing is, since you take iron pyrite, or maybe if you are taking the sulfur which is not pure, these particular thing will have a lot of impurities in them. So there will be a huge amount of impurities in FeS. Definitely FeS2 will have a lot of impurities because the ore. S may or may not be having impurity depending upon what kind of sulfur you are taken. And that is the reason you need to go through another process over here. The next process which is going to be here is going to be, so from here the sulfur dioxide, so from here SO2 is going to make through, go over here to into the purification area. So this is the purification chamber, and in the purification unit, we can say not chamber because they are not one unit, but there are totally 6 units. Okay, there are 6 units which are going to be there inside it. You need not learn these 6 units because they are just in part and parcel of the thing, but normally they don't ask, or the syllabus does not prescribe the purification part. But since we are using this particular process, we need to go through this particular thing right now. But as such, for learning, for exam point of view, you need not consider this particular thing for learning. So we have got over here from, so C, D, E, F, G and H. These are the chambers. There are 6 chambers which are going to be there in the purification unit. So the purification unit over here will be, the first one is you are removing the dust. So dust, there is a dusting tower. There is a dusting tower which will just ऊपर से steam डाल रहे हैं, so automatically dust particles will take in that particular steam and will become heavy and settle down. So that is how you are going to take care of the dust. So for removal of dust particles by downward blow of steam. The second is cooling tower, cooling pipe, for cooling the gas by passing through isolated pipe. So then the next one will be cooling pipe. So cooling pipe will be just, so SO2 whatever is generated, you want to cool it down. So to cool it down, you are using the cooling tower or the cooling pipes. Then comes the scrubbing tower for further removal of impurities and dust particles by downward spray of water. So whichever is, see, heavier particles, they absorb the moisture from the steam and then they settle down. But lighter particles or something which is not getting dissolved in water, the dust particles will remain. So that particular thing they are using downward spray of water. नीचे से spray डाला, so automatically the lighter particles are going to be removed. So for removal of impurities and dust particles by downward spray of water, then once this water का पूरा part हो गया, so it comes to the drying part. So that is a drying tower where dry moist gases by downward spray of concentrated sulfuric acid. Now we know concentrated sulfuric acid is a good drying agent, or in fact it's a dehydrating agent. That's why we are using this concentrated sulfuric acid to remove the moisture from the gas which has been generated over here. So gas में से moisture निकालने के लिए we are using this. Now it is quite a irony that for manufacturing of H2SO4 you are using H2SO4 as one of the raw material. Yes, it is there, but here it is not going to be used much because it's a drying agent. So it is just the gases will pass through it, so moisture is going to be taken out and the gas will pass. So H2SO4 is not actually used, nor it is coming in part of the reaction over here. It will come later on, but right now it is just acting as a drying agent. The next is arsenic purifier for removing arsenic oxide by passage of ferric hydroxide over ferric hydroxide. So this particular FeSO or even sulfur, we may have a certain amount of arsenic in it. Now the arsenic needs to be removed for sure because arsenic has the property to poison the catalyst. See, catalyst gets poisoned or they will be losing their property of catalyzation, or they are going to be damaged by arsenic as the impurity. So arsenic impurities needs to be removed from the SO2 gas which is already there. So that's why to remove the arsenic oxides, it is passed through ferric hydroxide. So ferric hydroxide will be used and it will be removing the arsenic. And finally, there will be a testing box in which, so the last part, that is H part, there will be a testing box where they will try to find out that whether the gas is pure or not. That will be done with the help of passing of light through a darkened box. So there will be this particular purity test done, and once the purity test is passed, it is going to go ahead. So the next thing is it is going to pass through a catalytic oxidation chamber. So now this SO2 is going to pass through a box over here, this thing over here, which is nothing but having 2 parts. That is the part I is nothing but catalytic oxidation chamber. Okay, so it will be catalytic oxidation chamber, that is a contact tower. That is, this is the one which is the contact process because of the contact tower. So in the contact tower, it is going to be having vanadium pentaoxide as the catalyst. The catalyst used is vanadium pentaoxide, and the temperature at which it takes place is around 450 to 500 degrees Celsius, and the at pressure is 1 to 2 atmosphere. So here what is going to happen is this SO2 is going to add oxygen to it in the presence of vanadium pentaoxide, and at 450 to 500 degrees Celsius and at 1 to 2 atmosphere, and get converted into SO3. So SO2 to SO3 is going to be formed with a good amount of heat also released. This is going to be taking place in the catalytic oxidation chamber, which is the contact tower. So in the contact tower, SO2, this is a very important part, that's why I'm repeating again. In the contact tower, it is the main process which is going to take place, where SO2 is going to get oxidized by oxygen to give you sulfur trioxide. So SO3 is going to be formed. And what is this catalyst? The catalyst over here is vanadium pentaoxide. The temperature is 450 to 500 degrees Celsius, and the pressure will be 1 to 2 atmosphere. So for catalytic oxidation, SO2 to SO3 by passage of the sulfur dioxide and oxygen through iron tower packed in vanadium pentaoxide, catalyst initially heated at 450 degrees Celsius takes place in this particular process. The next one is the absorption tower. So that one, from here it goes to the tower J. So tower J over here is the absorption tower. Now in the absorption tower, this particular vanadium, the SO3, what we got over here, is going to be added with another amount of sulfuric acid. So here it will be absorption of sulfuric vapors by descending stream of concentrated H2SO4. So here again the surprising part, that you are using H2SO4 as a raw material. Yes, here it is going to be used up. Concentrated sulfuric acid will be used in this particular place over here. So here it is going to be that SO3, right, plus H2SO4 will give you over here as H2S2O7, which is called as oleum. Okay, oleum or pyrosulfuric acid. So SO3 to H, this thing over here, this is in the we can say the production of SO2. This one over here is absorption, catalytic chamber. This one is absorption. And the last one over here will be coming up is the one which is dilution of oleum. So dilution of oleum, that is H2S2O7 plus H2O is going to give me. So here this thing is going to give me 2 H2SO4. You can see, so 1 H2SO4 we had used, but you are getting double the quantity. So automatically this SO3 has now got converted to H2SO4 by this particular method. So we are going to get, if we have used 1 volume of H2SO4 earlier in this stage, we are going to get over here 2 volumes of H2SO4, and that is nothing but dilution. So that we call it as K, chamber K, that is dilution of oleum to give you H2SO4. So that is how you get over here H2SO4. So these are the different steps which are involved during the contact process. So we will go through this one by one because there is a complete detailed thing which is given over here. So we see again step 1, chamber conversion, that is sulfur or pyrite burner. So chamber will be, this is sulfur or pyrite burner. So that will be a sulfur or pyrite burner which is going to produce SO2. So conversion is from production of sulfur dioxide by burning sulfur or iron pyrite. So the reaction is S plus O2 giving me SO2, or 4FeS2 plus 11O2 giving me 2Fe2O3 plus 8SO2. So this is what you are going to happen in this particular chamber. The next chamber, this chamber is not taken into consideration. That's why we don't have any detail in that particular part. We have got step 2 directly, which is this part, because this one is only for purification of this part. It is only the purification of SO2. This is not a part and parcel of the production unit. It is, if you are already getting a pure SO2, you can directly jump to this part. It is only because we are taking impure sulfur or we are taking impure Fe2S2, FeS2, that's why we are using this particular purification unit. So we come directly over here, that is catalytic tower or the contact tower. The contact tower, it is a catalytic tower oxidation where catalytic oxidation of sulfur dioxide takes place to form sulfur trioxide. So here the reaction is SO2 plus O2 in the presence of vanadium pentaoxide at 450 to 500 degrees Celsius at 1 to 2 atmosphere gives you SO3 and some amount of heat. So above reaction is an exothermic reaction, so hence it supplies energy. In fact, it is an energy supplier. Catalyst is vanadium pentoxide or platinum also. Platinum can also be used instead of vanadium pentoxide, but platinum pentoxide will be preferred. We will see why is it preferred in the later part. Temperature 450 to 500 degrees Celsius at pressure 1 to 2 atmosphere, and conversion ratio is 98%. So here the conversion ratio is very high. We saw in case of the ammonia that the conversion ratio is very low. That's why we had to repeat the process. We had to take that N2 and H2 and put it again in the first part. यहाँ पे conversion ratio is 98%. That's why you don't need, ऐसा कुछ नहीं होने वाला कि SO2 फिर भी बचा है and you have to put it back over here. जरूरत नहीं है. Because the conversion ratio is already 98%. So 98% conversion ratio is going to take place where 98% of SO2 is going to turn into SO3. That is in the catalytic oxidation chamber. The next is the third step, that is chamber is absorption tower. In the absorption tower, the absorption of the sulfur trioxide in 98% sulfuric acid to give oleum or pyrosulfuric acid is going to take. Now this is SO3 plus H2SO4 will give me H2S2O7. Now you will always be confused that इसमें directly water डाल के H2SO4 क्यों नहीं generate किया. So yes, remember this thing. I am going to clear that doubt also. We are going to have a point that why we are not using directly water and why we are taking the need of H2SO4 and why we are producing oleum and not directly adding water to it. So here we come to that also. So SO3 with H2SO4 will form oleum, that is H2S2O7. This is pyrosulfuric acid. So after this is formed, it goes into the last one, that is the dilution chamber, where you are adding water to this thing. As soon as you add water to it, it becomes twice the quantity of sulfuric acid which was being formed. So this way you are forming the sulfuric acid in the contact process. So the reactants are sulfur, iron pyrite, sulfur and in the or the pyrite burner. Catalyst vanadium pentoxide or platinum. Condition in the contact tower, temperature 450 to 500 degrees Celsius, pressure 1 to 2 atmosphere. Products in sulfur and pyrite will be sulfur dioxide, in contact tower will be sulfur trioxide, in absorption tower will be oleum, and in dilution tower will be sulfuric acid of the desired concentration. Equations as we see, S plus O2, SO2 or 4 FeSO2 plus 11 O2, Fe2O3 plus SO2. In the purification unit, there is no need of any kind of equations, but in contact tower is 2 SO2 plus O2 is going to give me 2 SO3 plus heat, and in case of absorption tower, it will be SO3 plus H2SO4 will give you H2S2O7, that is oleum, and next last one is H2S2O7 plus H2O giving you 2 H2SO4. So that is about the this part. Now we go in detail about the contact process का क्या चीज है. So first one we saw, when sulfur is burned in air, it burns with a pale blue flame forming sulfur dioxide and traces of sulfur trioxide. So that is why burning of sulfur or iron pyrite in oxygen is preferred to purified air, since heat energy is wasted in heating the unreactive nitrogen compound also. So we will normally try to take the oxygen directly, preferred और purified water, because ऑक्सीजन का डायरेक्टली ले लिया रहेगा तो हम लोग को नाइट्रोजन का 70% का हीटिंग का जरूरत नहीं पड़ेगा. सो दैट इज व्हाई वी नॉर्मली डू टू टेक डायरेक्टली द ऑक्सीजन. The second is purification. So impurities present in the gaseous form contains mainly dust particles, pyrite dust and arsenic oxides. So that's why you need to remove the impurities. So impurities, if not removed, tends to deactivate the poison the catalyst, and thereby reducing its efficiency. And method of removal will be dust particles will be done through the dusting and scrubbing towel, and arsenious oxides by the arsenic purifier, which contains FeOH thrice. That was purification. In the contact reactants, the gaseous mixture of sulfur dioxide and oxygen for catalytic oxidation of sulfur dioxide contains an excess of oxygen. So in the catalytic oxidation of sulfur dioxide to sulfur trioxide at elevated temperatures around 450 to 500 degrees Celsius, the excess oxygen favors the forward reaction. So yes, oxygen, much more higher quantity of oxygen over here will be favored, so that it is giving you the yield more easily. So, and moreover, the temperature is 450 to 500 degrees Celsius, thereby enhancing the yield of sulfur trioxide. In modern plants, oxygen from the air plant is employed. So yeah, in modern manufacturing places, they don't take air over here directly, they take oxygen, because there is an air purifying unit, वहाँ से oxygen लेता है और वहाँ से सीधा directly we give oxygen rather than air. Catalyst, vanadium pentoxide is preferred as a catalyst during catalytic oxidation of SO2. Vanadium pentoxide is preferred. I told you that vanadium pentoxide as well as platinum both can be used, but we are preferring vanadium pentoxide because it is preferred to platinize asbestos as a catalyst, since it is comparatively cheaper and less easily poisoned by susceptible to impurities. See, platinum is very susceptible to the poisoning by the impurities. So arsenic is going to give immediate effect on platinum, whereas it is delayed process in case of vanadium pentoxide. So accordingly, it is preferred to have vanadium pentoxide because of the impurities, and also mainly because vanadium pentoxide is much cheaper than platinum. Promoter used is vanadium pentoxide is compressed in shredded threads and mixed with the promoter, usually potassium oxide, to enhance the activity of the catalyst. So potassium oxide will be the promoter which is used in this case. Catalyst only initially heated. See, the catalyst over here will be initially heated because this is a exothermic reaction. So this reaction is exothermic. So initially it is going to be heated, but then it is going to be maintaining that particular temperature by itself. So the contact mass being porous facilitates access of the gas to the interior of the granules. The catalyst mass is only initially heated electrically, since the oxidation reaction, catalytic oxidation of sulfur dioxide is an exothermic reaction, and the heat produced maintains the temperature at 450 to 500 degrees Celsius. So because it is exothermic, it is going to maintain the temperature very easily by itself. We don't need to give additional heat later on. Only initially you will require to heat it. The temperature used in the catalytic oxidation is around 450 to 500 degrees Celsius. The catalytic oxidation of SO2 to SO3 is an exothermic reaction. So that's why it is going to give you per 2 molecules or 45 kilocalories. An exothermic reaction is favored. The higher yield is of the product sulfur trioxide by lowering the temperature. If the temperature is too low, the reaction may tend to slow down. So a rise in temperature by 10 degrees doubles the speed of reaction. So that's why, see, normally we try to reduce the temperature so that you are not wasting too much of fuel, but here if you decrease the temperature, then the yield will be decreased. So increase by temperature by 10 degrees Celsius increases the yield almost double. So that's why it is preferred to have an optimum temperature of 450 to 500, which is more suitable for catalytic oxidation reaction with the conversion of sulfur dioxide. So sulfur dioxide being about 98%. An optimum pressure of about 1 to 2 atmosphere is used during the catalytic oxidation of sulfur dioxide. In the catalytic oxidation reaction, SO2 to SO2, the increase in the pressure if a reaction takes place with decrease in volume, as in case of catalytic oxidation. So it is preferred, it is favored, the forward reaction is favored by increasing the pressure. If the reaction takes place with decrease in volume, as in the case of catalytic oxidation of sulfur dioxide, which takes place with the decrease in volume. So you can see that if I increase the pressure, the volume decreases. If the volume decreases, automatically the reaction becomes much faster, that the yield will be much more. So hence higher pressure favors a high yield of sulfur trioxide, but may cause damage to the lead pipes and acid resisting towers and decomposition of the porous catalyst. Therefore, an optimum pressure of 1 to 2 atmosphere is used. Now the last part about this thing is the absorption tower. Now I told you that why we are using H2SO4 over here and not directly adding water. So it is in the absorption tower of the SO3 vapors are absorbed in constant sulfuric acid and not in water. The reason is, even though sulfur trioxide is an acid anhydride of sulfuric acid, it is not directly absorbed in water to give sulfuric acid, because the reaction is highly exothermic, resulting in the production of a dense fog of sulfuric acid particles which do not condense easily. So when I am using water and I am adding that water into sulfuric acid, this reaction will be highly exothermic, and the reaction will be so exothermic that it is going to form dense fog of sulfuric acid, and this dense fog of sulfuric acid is very difficult to condense. So because it is very difficult to condense, that's why it is not advisable to add directly water to it, even though that it can give you sulfuric acid, but because of the highly exothermic reaction and due to formation of dense fog and which cannot condense, we are not using it. And sulfur dioxide vapors are dissolved in constant sulfuric acid to give you oleum, which on dilution with the requisite amount of soft water in the dilution tank gives sulfuric acid of the desired concentration up to 98%. So here once we get oleum, the oleum can easily be diluted by a particular amount of water and gives you the required quantity of H2SO4 of 98% concentration. Hence, we see that it is much more ideal to use this method rather than directly adding water to SO3. So this was about the contact process of sulfuric acid, a very important part, especially the last parts, which is why we are using not using water directly and using this thing, or why is the temperature this way, why is vanadium pentoxide used. These are some important questions in contact process. We continue with the other part of the chapter in the next video.